In this tutorial, I will go over and explain the settings that you'll find on the new simulation wizard. So first step is opening the wizard. In the Twedit, up here in the menu, you'll see CC3D project and then new CC3D project. Here you can give your simulation a name. You can use underscores and you can use numbers. You cannot use numbers in the beginning, and you cannot use spaces. So this is not acceptable because there is a space here, and so here you should use underscore, and this is not acceptable because there is a number in the beginning. So this would be acceptable. You can also choose a simulation directory, so go into browse and navigating to a directory where you want your simulation to be at. And you can also choose between Python plus XML. XML is a simulation specification language, and also Python only, where you do not have the XML. I highly recommend you always pick Python plus XML. And if you want to do Python scripting for running simulations on a cluster, for example, then there is another way, which is not this option. This other way, I'll leave the link in the description that points to the documentation on how to do a Python only simulation. This second option here is deprecated. So if you are using Twedit, I highly recommend you pick Python plus XML. Next, we have the lattice dimensions. By default, this is 256 for X and Y and 1 for the Z. This means this is a two-dimensional simulation. If you set Z to 2 or higher, this becomes a three-dimensional simulation. If you set both Z and Y to 1, this is a one-dimensional simulation. You can also choose boundary conditions of no flux and periodic. The difference between these two is this one. So no flux, the borders act as hard walls. The cell cannot go through the borders. And periodic boundary condition, the cell can go through one border and reappear on the opposite. If a certain dimension is size 1, you cannot set the boundary condition to periodic. So generally this is a two-dimensional simulation, and Z is 1, which means Z can only be no flux. If you set Z to periodic, you will get an error. And you can also set different boundary conditions for each dimension. So for example, no flux for X and periodic for Y, and vice versa. Next, you can choose between square and hexagonal lattice type. The square, as the name suggests, the pixels are squares, and in the hexagonal, the pixels are hexagons, but that's only for two-dimensional lattices. In 3 dimensions, the square voxels, which is a name we use for volumetric or 3-dimensional pixel. So the voxels will be cubes, and if you pick hexagonal, the voxels will be hexagonal prisms, as in this picture here. So you can see how differently they will behave. The hexagonal prism has different symmetry in the XY plane compared to the Z direction. So this might not be suitable for 3-dimensional simulations unless your XY dynamics is inherently different from your Z dynamics, for example, in an epithelium. So in general, we recommend using square lattice unless in 2 dimensions you are trying to avoid lattice spinning. In this case, hexagonal is better, but square, you can more easily interchange your simulation between 2D and 3D without worrying too much about contact energies. Moreover, if you change from square to hexagonal and vice versa, you have to be aware that surface constraints and contact energies will behave differently, so you have to adapt your parameters. Next, average membrane fluctuations, as the name suggests. This increases the fluctuation on the border of the cells. This is also called temperature because of a legacy of statistical mechanics in the development of the cellular Potts model. Now the pixel copy range, this is the size of the neighborhood around the source pixel that the cellular POTS model can choose for a pixel copy attempt. So neighbor order of 1 allows the cellular POTS model to pick pixels around the source pixel that are above, below, left, and right. If you go to a neighbor order of 2, now you can pick pixels above, below, left, and right, and also for the diagonals. So it will be 8 pixels in total. In practice, the difference between the neighbor order 1 and neighbor order 2 is that you are reducing the lattice spinning when you increase the neighbor order. However, you are also decreasing locality and decreasing simulation performance. That's why we usually choose either 1 or 2, and very rarely we go above 2 because the simulation becomes less local. You are allowing the cells to effectively copy pixels beyond their borders, which makes the cell structure less cohesive. Last, we have the number of Monte Carlo steps. This is the length of the simulation. And the initial cell layout, you can choose between a rectangle of cells, a blob of cells, like a circle, and you can also customize your initial cell layout using a PIV file. Next, you can define your cell types. So here you just write your cell type, for example, cell 1, and click Add. Same rules apply here. You cannot use spaces, so this is not acceptable. If you want to write multiple words, I suggest you use an underscore or start the next word with uppercase letter. You can use numbers, so this is acceptable. You cannot use numbers in the beginning, so same rules apply here. You can also freeze cells. Also here in the table, clicking freeze. What freeze does is if a cell is frozen, it doesn't move at all in the simulation. Next, chemical fields. Here, the same as before, the same as in cell types, you write the name of the field. Here you can select among options of diffusion solver algorithms and then press enter or hit add. The field will show in the table up here. Among the options, we have fast diffusion solver for 2D specifically. We have steady state diffusion solver, which is recommended if your diffusion coefficient is extremely high and you just care about the steady state and not the transient of the field. But in general, we recommend the diffusion solver FE. This one is optimized, works in 2D and 3D, and it allows you to capture the transient of the field evolution. So if you want to select another one, for example, steady state, you click here and then hit add, and then it will show in the table the name of the field and the corresponding solver. Finally, cell properties and behaviors. Here is where you define what are the properties and behaviors the cells will have. For example, in the adhesion behaviors, you can set your cells to have adhesion energies with other cells, which regulate affinity between cells. Contact internal is the same, but when you have cluster of cells, you can distinguish what is a contact energy between cells that belong to a cluster and cells that belong to different clusters. Adhesion flex is similar to contact energy, but allows you to regulate how the contact energies behave pairwise and for different cell IDs, depending on the situation, depending, for example, on the concentration of a certain field. Compartments is the same as having contact internal. Then focal point plasticity, this allows you to set spring-like forces between cells. Chemotaxis allows cells to migrate towards or against a chemical field gradient. Secretion allows cells to release substances and add material to a certain chemical field. Growth allows cells to grow. it requires you to set this one, to check this one, volume local flex. The volume local flex allows you to set volume constraint for the cells. If I uncheck this, you see that there are two options, volume flex and volume local flex. The volume flex sets a volume constraint depending on cell type. However, if you want different cells of the same type to have different volumes, then you want to check the volume local flex, which allows you to regulate individual cell volume constraint. Same thing for cell surface, so surface flex for a single cell type, and local flex you can regulate the surface constraint for individual cells of the same type. You can, by checking the mitosis, you allow cells to divide, and so from one cell you have two cells. Death, this one allows the cells to shrink and disappear. On the external force, you can set a constant external force applied to cells of a given type, or the local flex option allows you to set external forces for individual cells, even if they are the same type. Then down here we have length constraint, and same thing, local flex for individual cells. So the length constraint allows the cells to acquire a more ellipsoidal shape instead of a round spherical shape. In general, when we include the elongation constraint, we also use a connectivity global because the connectivity basically penalizes a copy attempt of pixels that break one cell in two pieces. So you in elongation, you want your cells to be long, but you also don't want to have cells breaking in two pieces, which can happen depending on the parameters you set for the elongation. So usually we implement elongation with a connectivity plugin. Up here we have trackers. So these trackers, for example, center of mass and cell neighbors, they allow you to visit the center of mass of a cell or the neighbors of a cell. So if you uncheck this, for example, if I uncheck cell neighbors, I cannot do a for loop over cell neighbors. I need to have this one included in my model. Of course, this comes at the expense of simulation performance, because at every step, the CompuCell3D will have to recalculate all the neighbors of all cells, all the centers of mass. You can also, by checking this option, moment of inertia, you are tracking basically the shape of the cell. Cell pixel tracker tracks the pixels, all the pixels of all cells, so you can visit them and do a for loop over cell pixels. And the cell boundary pixel tracker tracks the pixels of the border of the cells. So if you are just interested in looping over the pixels of the border of the cell, you don't need the cell pixel tracker. You can directly use the cell boundary pixel tracker. Now, if you set a secretion plugin, you can specify secretion rates based on cell types and based on the field you want. So for example, here I can choose cell type of cell 1 to secrete a certain field. For example, this is VEGF1. I specify a secretion rate and select the secretion type. So if it's uniform, it means that every Monte Carlo step, the field is locally added 1 unit of material. So by hitting add entry, it appears up here, and you can double check your settings. So field of VEGF1 is secreted by cell 1, rate 1, and type uniform. On contact means that there is a condition for secretion. So if cell 1 is on contact with epithelial cell, and then you hit this button add on contact, just to write, this button just writes whatever is in this menu, writes in this blank field. So here, if I do add entry, you can see that the rate, again, this is uniform rate of secretion on contact with epithelial cell. This means that cell 1 will secrete VEGF at a rate of 1 if the cell 1 is in contact with an epithelial cell. Finally, constant concentration is different. Instead of every Monte Carlo step adding material to the field, it holds the field at a certain value. So no matter what's going on, the cell 1 will always hold the field concentration at value 10. By hitting add entry, you can see here type constant concentration at value 10. This is being held by the cell. Of course, I cannot have this because these are all contradicting information. So if you want to delete a row, you can just click remove rows. You select the row and click remove rows. And if you want to start over, you can clear table and start over. Next, if you set a Chemotaxis plugin, here you first select the field. You want a cell to undergo chemotaxis towards or against the gradient. You set a lambda constraint. This one is basically the strength of the chemotaxis force. So if you set a positive lambda, this means that your cell will go up gradient. If you set a negative lambda, your cell is going opposite to the gradient direction, so it's trying to run away from the field. You select your cell type. So here, for example, cell 1 undergoes chemotaxis towards the gradient of VEGF with a certain strength. And you can also select whether it only undergoes chemotaxis towards a certain cell type. So for example, if I set only undergo chemotaxis towards medium, it means that it will not push the epithelial cells even if the gradient is positive at the border with an epithelial cell. So if I check medium here, I click this chemotaxis towards, again, just to write the name of whatever is in this menu. And then add entry. You'll see the specifics here. So cell type 1 undergoes chemotaxis, up gradient with a strength of 10. The corresponding field is this VEGF. And you only allow chemotaxis to occur if the target pixels are medium pixels. And there is also this type here, regular type. There are other types of chemotaxis, saturation and saturation linear. However, I would say these ones are not properly implemented, so I won't explain what they actually do. What they try to do is to alleviate exponential forces on the cells, because sometimes gradients are exponential because the field has a decay. In this case, you can have overwhelming forces on the border of the cells which can destroy the cell. In this case, we use logarithmic chemotaxis, which we set on Python by hand, and neither of these options do that. So I will ignore those for now, and in another tutorial on the specifics of chemotaxis implementation in CompuCell3D, I will explain better how to implement either a saturation chemotaxis or a logarithmic one. Next, the Adhesion Flex plugin. Here you specify two molecules that, depending on the concentration, it regulates the affinity between two cells. So for example, let's suppose I have a receptor, or I don't know, a binding molecule mol1 and mol2, and then I have to define a formula for these molecules. By default here, it's getting the minimum value between molecule 1 and molecule 2. Again, because these names have to be the same, so if I give names mol1 and mol2, these ones have to be mol1 and mol2. So this formula is basically getting the minimum value of mol1 and mol2 for the respective cells. This is not usually what's done. Usually it's the product, because you are assuming a mass kinetics where you model the probability of the two molecules interacting and binding, and creating that contact affinity between the cells. So usually we do multiplication of the two molecules, but you can also set other molecule types here and do more complex formulas. And these are all the settings. If you have questions, please go ahead and ask in the comments. Or better yet, go to the CompuCell3D subreddit. There is a higher chance we'll help you there.